In the second screencast, I'm going to talk about conversion stoichiometry and what that has to do with reactor design or reactor sizing. So first of all, stoichiometry, as we're well aware, we can write for any reaction the sum of stoichiometric coefficients multiplied by species equals 0, where the stoichiometric coefficients will be negative for reactants and positive for products. So for example, if we have A molecules of A reacting with B molecules of B to make CC and DD, the stoichiometric coefficients are negative A, negative B, positive C, and positive D. For instance, we're well aware of this phenomenon. Now conversion has already been defined as well. One thing that we can do is to select one species as a basis for calculation. We have to do that in order to use a conversion. And for example, we can divide by the stoichiometric coefficient of species A. It doesn't have to be A, but we can always, since we're just speaking in general terms, we could define the reference compound to be A, and then the stoichiometric coefficients of everything else get divided by the stoichiometric coefficient for A, or the magnitude of it, to be exact. And we can write the conversion being the moles of A reacted over the initial moles of A. So in terms of symbols, X, and in Hill, it's F, lowercase f is used for fractional conversion. This would be Na naught minus Na over Na naught. And so Na at any given time is Na naught times 1 minus the conversion, the number of moles of A. And for any other species, we can take the initial number of moles minus the stoichiometric coefficient for that species over the stoichiometric coefficient for A times the initial number of moles of A times the conversion. So a conversion will give us a way for any reaction to say how many moles of every species we have, which is the advantage. So with this conversion concept in mind, for a batch reactor, we can look at what the mole balance looks like for a homogeneous isothermal system. From the last screencast, we had the rate of change of the number of moles of a species is given by the rate times the volume. And if we work in terms of conversion, the number of moles is given by this expression. So the initial number of moles times 1 minus the conversion. And then, so if we carry out the differentiation, of course the derivative of that is 0. So this is equal to the initial number of moles times the opposite of the rate of change of the conversion. So with that, we can rewrite our mole balance as the initial number of moles times the rate of change of conversion equals the opposite of the rate of consumption, or the rate of production of A times the volume. And we can reorganize this equation to look like Na naught times the integral from 0 to x of dx over negative Ra is equal to the integral from 0 to t of the volume. And if the volume is a function of time, then this expression is useful. For example, if we apply a piston which is moving so that we know how the volume varies with time, we can use this expression and integrate. Of course, if the volume is constant, this is very easy to integrate. Either way. If the volume is a function of conversion, another useful way to write this expression is before doing the integration to move the volume over to the left-hand side of the equation, and then we can express the integral on the left-hand side entirely as a function of conversion. This only makes sense if V depends on conversion. But if we do that, then the initial number of moles times the integral of 1 over the rate times the volume, the rate of consumption of A times the volume, is equal to time. So this allows us to relate time to conversion, or vice versa. If we have flow, we can go back to our general mole balance to figure out what to do with conversion. Now, the opposite of the rate of generation of a species is the moles of A reacted per time. And we can express this as the moles of A reacted over the moles of A fed multiplied by the moles of A fed over time, because we just multiplied and divided by the same thing. And by definition, the first term is the conversion, and the second term is the initial flow rate of A into the reactor. So when we use this relationship, we can rewrite our mole balance as Fa naught plus the rate of generation being equal to Fa. So Fa, the flow rate of A, is equal to Fa naught times 1 minus x. So we can use this. It's very similar to actually the number of moles expression in terms of conversion. And so the initial number of moles, the initial flow rate of A is equal to the initial concentration of A multiplied by the volumetric flow rate into the reactor also. That can be a useful relationship to use. So with these relationships in mind, for flow reactors, the CSTR design equation, ends up looking like the volume being, this is what we had before, the initial flow rate into the reactor over the rate of consumption of A. We can write that as the conversion times the initial flow rate into the reactor over the rate of consumption of A using the exit conversion. For a plug flow reactor, we have that the differential of the flow rate of A over volume equals the opposite of FA naught times the rate of conversion, and that's equal to the rate of reaction. So the volume of a reactor can be written as the initial flow rate times the integral from 0 to x of 1 over the rate of consumption of A. And for a packed bed reactor, it's an analogous expression with weight instead of volume and the rate of consumption per unit of mass. So with that in mind, we can develop Levenspiel plots. Levenspiel plots are useful because they allow us to design either CSTRs or plug flow reactors. The way that they're written is the rate of 1 over the rate of consumption of the reference compound, so species A in this case, versus the conversion of that same species. And so based on the design equations, well, of course we've got, if we're interested in x naught equal to 0 and the outlet conversion being 0.8, we can look at different types of reactors. So for a CSTR, based on the design equations, the volume required would be the initial flow rate into the reactor multiplied by the area of a rectangle that's defined here. So the area of the rectangle going from here to a conversion of 0.8. And the reason for this is that the rate of reaction just depends on the final conversion. So it's this point that really matters in the CSTR. So we multiply the conversion times 1 over the rate of consumption at that final conversion. For a plug flow reactor, on the other hand, it's the integral that matters. So I can delete this. So we take the integral under the curve, going from a conversion of 0 to 0.8, and that tells us, and multiplying that by the initial flow rate tells us the volume that we need. So Levenspiel plots are a convenient way to directly compare plug flow reactors and CSTRs, and to design them both. Notice in this case that the volume required for a plug flow reactor is less than that for a CSTR, and this is true as long as the curvatures, well, it's not just that the curvature is positive, but the rate of consumption, or 1 over the rate of consumption, is always increasing as conversion increases. That doesn't have to be the case, by the way. Now, for CSTRs in series, it helps to define conversion in terms of the feed to the first reactor. We don't have to do this. We could define a different conversion for every reactor, but by convention, to make things simple, we're going to do this based on the first reactor so that we can make comparisons between one reactor or 2 reactors or 3. So if we do that, the flow rate leaving the first reactor is given by FA naught, so that's going into the entire series of reactors, times 1 minus the conversion from the first reactor. And then the flow rate leaving the second reactor is the initial flow rate into the entire series, so that stays the same, times 1 minus the conversion leaving the second reactor. The mole balance at steady state for the second reactor then looks like this. This is just based on the mole balance for any reactor. And it tells us that the volume for the second reactor is FA1 minus FA2 over the rate of reaction in the second reactor. And that's equal to FA naught times the difference in conversion between the second reactor and the first reactor over the rate of consumption of A in the second reactor. Another way to express this in terms of a Levenspiel plot is that the volume of the second reactor is the flow rate entering the first reactor times the area of a rectangle between x1 and 0 and x2 and the rate of reaction leaving the second reactor. Or if I go back to the Levenspiel plot, where are my, here we go. So if I go backwards, that would mean that if, for example, I was interested in the volume of a reactor going from 0.4 to 0.8, I would just draw this rectangle and multiply by the initial flow rate going into the first reactor, is another way of saying that graphically. Now going back to where I was, sorry. So the volume for any reactor is the initial flow rate times the area of a rectangle between xi and I minus 1 and 0, and xi and the rate 1 over the rate of consumption leaving that reactor. So Levenspiel plots are a really convenient way of comparing a single plug flow reactor, a single CSTR, multiple CSTRs, a plug flow reactor followed by a CSTR in series, a CSTR followed by a plug flow reactor. There are all sorts of series that we can consider. And notice that in the limit, of an infinite series of CSTRs, the plug flow reactor volume is obtained, because we basically end up with the integral under the curve. One thing that's also useful for reactor design that Fogler uses are stoichiometric tables. This is something you can easily develop based on what we know about stoichiometry and conversion. The idea is that we write the number of moles of each species in terms of conversion. So for species A, that's easy to do. For species B, for instance, we have the initial number of moles of species B minus B over A times the initial number of moles of A times the conversion, and all of the expressions look similar for all the other species. We also can write a total number of moles, which is the total number of moles initially, plus a series of expressions that have to do with all the stoichiometric coefficients, times Na naught times x, and it allows us to write delta. This lowercase delta tells us the net change in the number of moles relative to the stoichiometric coefficient for A. So the total number of moles is the sum over all species of the number of moles of each species, and delta is the sum over all species of the stoichiometric coefficient for that species over the opposite of the stoichiometric coefficient for A. If we have flow reactors, we can write the rate of consumption of A over A being the rate of consumption of B over B, and so on. So all these terms are equal if we write the rate of reaction of A over its stoichiometric coefficient. All of those terms are equal. We can define the space-time as the volume of a reactor over the flow rate entering that reactor, the volumetric flow rate, and the symbol for that is tau. That's common in reactor design. And so, for example, the plug flow reactor design equation can be rewritten as the space-time tau being the volume over the initial volumetric flow rate, and that's equal to the initial molar flow rate divided by the initial volumetric flow rate times the integral from 0 to x of dx over the rate of consumption of A. And so we can also write that as the initial concentration of A times this integral of 1 over the rate of consumption of A. We can also define a space velocity as being the initial volumetric flow rate over the volume, and that's 1 over tau. And because the rate of reaction of A is a function of concentration, the design equation can be written from the concentration of A being Ca naught times 1 minus conversion. And that's a convenient way to work. So tau is given by the integral from Ca to Ca naught of 1 over the rate of reaction of A in terms of concentration also. If the volume is not constant, then the concentration is not actually equal to this expression. This is only true if volume is constant. So in order to deal with that, we think about how volume depends on conversion. We can define capital theta I to be the initial concentration of a species that's entering the reactor over the concentration of A entering the reactor. So the flow rate of species A, the molar flow rate, is given by the initial flow rate times theta I minus the ratio of stoichiometric coefficient to the stoichiometric coefficient of A, anywhere. This should be A, by the way. And if the volume is constant, the volumetric flow rate equals the initial volumetric flow rate. So the concentration of a species is given by the molar flow rate over the volumetric flow rate, which is Ca naught times theta I minus the ratio of stoichiometric coefficients times the conversion. However, if that's not true, we need to consider how the volumetric flow rate depends on the conversion. So in that case, in liquids, we don't really have to worry about this very much, and we generally ignore this. But in gases, we can't neglect the dependence of volumetric flow rate on conversion, necessarily. If we use the gas law, we can write the volume at any point as the initial volume times the initial pressure over the final pressure, times the temperature over the initial temperature, times Z over, that's the non-ideal factor, over the initial Z value, times the total number of moles over the initial total number of moles. Assuming that PT and Z are constant, NT changes if there is a net gain or loss in the number of molecules. If we let delta equal this sum over all species of the ratio of stoichiometric coefficient to the initial, the stoichiometric coefficient for A, that gives us the net moles produced per mole of A consumed. And by definition, we can write the total number of moles as the initial total number of moles plus delta times Na naught times X. It's also convenient to write this as the initial total number of moles times 1 plus delta times Na naught over Nt naught times X, and that can be written as nt naught times 1 plus epsilon.